We should start the final talk before lunch. This talk is also going to be about or related to point-free topology. And our speaker is Ranjita, last name, Raviprakash.
Yeah.
Thank you.
Thank you. Hello everyone. I would really like to thank the organizers for the support because of which I'm here, and also I would like to thank Department of Mathematics, New Mexico State University for the support. This is joint work with Guram Bezanishvili and an alternative approach to point-free topology. I'll start off with the background. So point-free topology is basically study of topological spaces by the means of open sets. And so we have a very well-known dual equivalence. Here, top is the category of topological spaces and continuous maps. FRM will be category of frames with frame homomorphisms. SOB is category of sober spaces, and SFRM will be category of spatial frames. The omega here is a functor which takes a topological space and takes the open sets of a topological space, and we get a frame. To go back, PT is a functor which maps a space of completely, which takes a frame and maps a frame to its space of completely prime filters. But there are different approaches to study point-free topology. In fact, Kuratowski studied power set algebra equipped with interior operators back in 1922, and later on McKinsey and Tarski generalized this concept to interior algebras in 1944. So I will be considering this direction and looking at the approach of McKinsey-Tarski's approach. So what is interior algebra and what is interior operator? Interior operator is an operator on a Boolean algebra such that it preserves top, preserves meet, and it is decreasing, and it is idempotent. Interior algebra is a Boolean algebra with an interior operator. And in order to motivate the definition of what empty algebras are, McKinsey-Tarski's algebras, I just want to give an example what is an interior algebra, example of an interior algebra. If X is my topological space, power set of X equipped with the topological interior is an interior algebra. If I have a continuous function from between topological space X and Y, the F inverse from power set of Y to power set of X is a complete Boolean homomorphism satisfying F inverse of interior of A is inside interior of F inverse of A. If I let my F to be open, I actually get an equality, but I'm more interested in continuous functions, so I'll just keep the inequality. And by this example, motivates our McKinsey-Tarski algebras, which are empty algebras. It's a complete Boolean algebra with an interior operator box, and the morphisms are empty morphisms. It's a complete Boolean homomorphisms, such as H, M to N, satisfying H of box A is below box H of A for each A in M, very similar to what we get in topological spaces. So empty will be my category of empty algebras and empty morphisms. So we already have a very known dual equivalence between frames and topological spaces. So our goal is to try to fit in the puzzle of that and see where our empty algebras act with frames and how they act with topological spaces. So how to go from empty algebras to frames? If I have an empty algebra M, I take the opens of an empty algebra. Opens are just fixed points of my operator box. And I'm calling the collection of all the open elements to be O of M. In fact, this O is a functor, essentially surjective functor from empty algebras to frames. In order to show this is an essentially surjective functor, actually we take a frame, we take the Boolean envelope of the frame, and we take the McNeil completion of the Boolean envelope, and we get empty algebras. So that's what we use to show it's essentially surjective, but it's not faithful nor full. So moving on, in some of the subcategories of empty algebras, we will see when it is actually full and faithful. So how to relate our empty algebras to topological spaces, as our whole definition of empty algebras was inspired by topological spaces. So my P power set, P, it's a functor, contravariant functor from topological spaces to empty algebras. such that the diagram commutes. In fact, this is very true because the open sets of a topological spaces are fixed points of an interior, topological interior operator. So that's why the diagram commutes. And how to go back? How to go back from an empty algebra to topological spaces? By taking the atoms of an empty algebra. And we define the topology by the mapping eta. It's from empty algebra to power set of atoms of M. It's defined like eta of A is all the atoms below the element A. In order to define the topology, I take the collection of eta of open elements. That will be my topology on the atoms of M. So this AT is my contravariant functor from empty algebras to topological spaces. Now, if I define mapping from X to atoms of power set of X, atoms in a power set are singletons, so epsilon of X is singleton X. This epsilon is a homeomorphism. So now my P and AT is a contravariant adjunction with units eta and epsilon. If I take my empty algebras to be atomic, I'm calling it to be spatial empty algebras. So now the adjunction we have will be equivalence if we restrict the empty algebras to spatial empty algebra, because the eta what we had before will be an isomorphism if and only if M is spatial. So the adjunction becomes an equivalence when we restrict it to spatial empty algebras. This, in fact, generalizes the duality between complete atomic Boolean algebras and sets. So in order to compare the what is happening here with what we had with frames, so we get a dual equivalence between spatial frames and sober spaces. So here we have dual equivalence between spatial empty algebras and topological spaces. So it is very easy for us to capture the lower separation axioms which we cannot cover, which comes before sober spaces. We can cover all the lower separation axioms here. And to do that, so I'll be defining lower separation axioms on my empty algebra by looking at how tightly these open elements sit inside my empty algebra. To begin with, I just want to recall the definition of joint generation. We say a subset S join generates an empty algebra if each element of an algebra can be written as join of elements from S. In fact, the singletons usually are join dense in a topological space, or join generates the topological space. But in our case, we may not have the atoms. So what we are trying to do here is, we try to see how the atoms in each separation axioms can be rewritten or acting like, and we try to find the sets, subsets, or identify the subsets in my empty algebra, which resembles how the singletons act in topological spaces and join generate them. For example, in T0 space, every singleton is closure of itself, intersection, saturated set. Saturated set here I mean arbitrary intersection of opens. So I generalize this to an empty algebra setting. An empty algebra is a T0 algebra if the meets of a closed element and a saturate element join generates M. So instead of X closure, which is a closed set, I'm taking a closed element, and exactly like how we have saturated set, I'm taking the saturated element, so join generates M. So, and this makes this T0 separation axiom makes our O functor, which we defined in the beginning, faithful. And moving on to the next separation axiom, it's a soberity. We say an empty algebra is weakly sober if each join irreducible closed element P, there is an atom X such that P is diamond X. Diamond here is dual of box. It is negation, box negation. And we are saying an empty algebra is sober if it is T0 and weakly sober. A quick remark, if I have a sober empty algebra, then each join, closed join irreducible P, there is a unique atom which makes the P is equal to diamond X. In topological spaces, the converse is also true, because the moment you have uniqueness, it gives us T0, but it is not the same in empty algebra setting. So the converse need not be true in our empty algebra setting. So now we have defined sober empty algebras. Now we can compare the space of atoms and space of points of opens of M. Points, I mean completely prime filters of opens of M, by defining my theta to be upset of atoms. So this eta has a homeomorphism if and only if M is weakly sober and atom of M is a T0 space. And now we get the O functor what we had before to be equivalence when we restrict it to sober empty algebra to spatial frames through the following commuting diagram. So next we have T-half separation axioms, or also called, I think it's called TD spaces also. So we say how does the singletons look like in T-half spaces? Each singleton is locally closed. Locally closed meaning it is an intersection of an open and closed set. So we do the same thing with the empty algebra setting. I generate my empty algebra, join generate my empty algebra by locally closed elements. And that kind of algebra are called as T-half algebra. So this T-half algebra is really, the definition immediately gives us that an empty algebra is T-half algebra if and only if it's isomorphic to the McNeil completion of the Boolean envelope of opens of M. And also, interestingly, this separation axiom also gave us this theorem. If M is sober, T-half algebra, then M is spatial if and only if opens of M is a spatial frame. So when M is spatial, O of M is always spatial. So, but the converse is not always true. So by adding sober and T-half property, we get the converse part also to be true in this case. And then next we have T1 separation. T1 space, it's very well known that every singletons are closed in T1 space. So the moment I have to define my empty T1 algebra, so closed elements join generates this T1 algebra. And then we want to now, our goal is to see how all the axioms we have created acts with the frame axioms and the topological space separation axioms. So one of the invariant which is close to T1 in frames is subfit. A frame is a subfit if A is not below B, there exists an element C such that A join C is 1, but B join C is not equal to 1. So if I have an empty algebra and opens of M, it will be subfit. But the converse need not be true. But when we add an extra condition that if my M is T-half and opens of M is subfit, we get our empty algebra to be T1. This is about T1 separation, and then we move to the Hausdorff separation. So in Hausdorff spaces, every singleton is intersection of regular closed sets containing it. So following the same pattern, we generalize it to our empty algebra. We say an algebra is Hausdorff algebra if meets of regular closed elements join generates the algebra. And very similar to what we find in topological spaces, every Hausdorff space is sober. We get the same result here. Every Hausdorff algebra is sober. And in order to compare the Hausdorff algebra to Hausdorff frames, there are many equivalent conditions for Hausdorff frames. The one I have picked is this one. A frame is Hausdorff frame if for any AB in frame with A naught below B and A naught equal to 1, we can find elements U, V such that U is not below A, V is not below B, and U meet V is 0. So if I take an Hausdorff algebra, and the opens of that Hausdorff algebra will give me a Hausdorff frame. But here again, the converse is not true, but I'm trying to add the condition T1 on M and see if I may get the converse. I've still not proved it, but I'm just still trying to prove it. This is about Hausdorff, and next we move to regularity. So a frame is regular if every element is join of elements well inside it. Well inside is rather below, and I saw Rick Ball's definition, and I think that is a better definition. So if you have A is right below B, then there exists a C such that C meet A is bottom and C join B is top. And equivalently, this is also a definition where I'm using pseudo complement here. Pseudo complement join A is 1. Then from regularity onwards, we are very close to the axioms what we find in frames. So from here onwards, it's very it coincides with the axioms we have in frames. So in empty algebra setting, I say A is well inside B provided the diamond A is below box B. So if I take my elements of M to be open, if I take the open elements and if A is well inside B, if and only if A is well inside B in frames. That is, if they are on the open elements, they both coincide. Well inside in the frames is same as well inside in my empty algebra. So, and I say an algebra is regular if it is T1 algebra, and every open element can be written as join of open elements well inside it, which you can see it's like now from now on we are very in coinciding with the frames real separation axioms. So again, we can easily prove that if M is a T1 algebra, then M is regular if and only if O of M is a regular frame. As I said, from now onwards, we will be in one-to-one correspondence with frames. Now, next is complete regularity. So complete is inside relation is very similar to again what Rigbol has on the board. I think that's a good definition. So I am denoting it by slightly different notation just to be say that this is happening in empty algebra. I say C is well inside D if we can find a family or a collection of elements AR in M enumerated by rationals in 0 and 1, between 0 and 1, such that C is below A0, A1 is below D, and for any rationals P less than Q, AP is well inside AQ. So here again the definition of completely regular empty algebra is it should be T1 algebra, and every open element is join of open elements completely inside it. And then we get this theorem: if M is a T1 algebra, then it is completely regular if and only if opens of M is a completely regular frame. So the last separation axiom is normality. We say an empty algebra is normal if it is T1 and for any closed elements such that C meet D is 0, we can find open elements UV such that U meet V is 0 and C is below U and D is below V. So as we moved on to the higher separation axioms, we are very close to how it looks in normal topological spaces. And if M is a T1 algebra, then M is normal if and only if opens of M is a normal frame. And normal space usually implies completely regular. So we wanted to prove something very similar here also. So we used Urizon's lemma, what we find in topological spaces, very similar one for empty algebras. So if you have a normal empty algebra and you have there is a closed element below an open element, there exists a family of open elements such family of open elements UP such that C is below U0 and U1 is below A, and if P is less than Q implies UP is well inside UQ. So the moment we prove this, we can easily prove that if M is normal empty algebra, M is completely regular. So okay, in order to summarize what I just did now, we have T0, we have sober, and we have T half. From T1, T1 implies subfitness in frames, Hausdorff implies Hausdorff frames, and from regular, completely regular, and normal, we are in one-to-one correspondence with empty algebras and frames. Thank you.
Are there any questions for Ranjita? Well, let's thank her again. Our next activity is lunch. in 10 minutes. Would you like to say something?
Just that I don't think we need to wait 10 minutes. So lunch is provided as part of your registration fee for the conference. There are little boxes out there. Some of them are vegetarian options. There are a few options. I think all the boxes will just grab what you want and see. I think